elements that the main elements that participate in any acidizing or stimulation job. I mean the things that makes the job successful or make it failure. Okay. So stimulation, by its like definition, it's a treatment. I mean, any kind of treatment that is performed to restore or enhance the productivity of a well. And actually, it's quite important to know that we can apply this kind of treatment in different stages of the field life. Sometimes we can start right after the drilling. I mean, we can do stimulation just after the drilling, or we might do the treatment after years of production. I mean, this is depends on your case. It depends on the policy of the company and depends on the policy of your organization. Um, Mainly, stimulation treatments fall into two main groups, either hydraulic fracture. I mean, this kind of treatments that are performed above the fracture pressure of the reservoir formation and create highly conductive flow path between the reservoir and the well bore. And the matrix stimulation is designed to treat the near wellbore reservoir formation rather than goes deeply into the formation, and with a pressure less than the fracture reservoir pressure. So that's why they call it matrix. And there are many problems that we are facing in our in the oil industry every day, and and these problems that like not all the problems are being recovered or being overcome by well stimulation, because sometimes it's not necessary to do acid or fracturing to overcome these problems. There are other groups of stimulation treatments, includes let's say sand control. And in the sand control, we do actually prevent the migration of reservoir sand into the wellbore or near the wellbore area. And sometimes the problem is about water controlling. So we can control the water that is being produced, and there are different means of controlling water, as we will see in this presentation. And sometimes we just need to do like a wellbore cleanup using, let's say, acid wash. And the acid wash, it doesn't go deeply into the new formation, while it's cleaning the wellbore and removing if you have any scales build up, preventing any flow from the reservoir into the wellbore. So this is the general overview about stimulation and the main types of stimulation. Here we have the history of acid. In fact, acidizing is not exactly a new technology. I mean, the first acid treatment was ever done in 1895, which was like by Ohio Oil Company, and it was fairly successful. And they had the hydrochloric acid treatment. But the thing is, they had corrosion problems. In the essence, they forgot that iron steel is soluble in hydrochloric acid, and they experienced like a severe problems in tubing. So it took almost another 40 years before the second acid, was done. So the corrosion habitus was devolved actually more or less in 1932, and it devolved later on. The main drive came like actually in 1980s, when was extensive research done and improved our theoretical understanding, and the result we have the fluid and the acid completions. And after that, essentially this century, it really started a computerized design and execution support of acidizing treatments. And this is, as you can see here, a picture of a third, it was about like 30 earlies in the acid treatment. For those who are aware of it, it says that already the name of Dowell, and this is the company that was set up by Dow Chemicals and was later on, it was taken over by Schlumberger. For a while, it was known as Dowell Schlumberger, then became Schlumberger Dowell, and now the well just disappeared and only Schlumberger. So you can see here the equipment is quite simple, where we have the pump truck and the little hose, and it's connected to the wellhead. So as you can see here, it started a long time ago in 1895, and the main or the big revolution in the theory of acidizing was mainly about in 1980s. So basically, there are three types of acid treatments, and it depends on the level of the damage and how much the depth of penetrations, is needed to stimulate the well. So in acid washing, for example, the objective is simply the tubular and the wellbore cleaning. I mean, the treatment of the formation is not the main goal of acid wash, and the acid wash is often used or performed to clean out the scale and the other thing, anything that restricting the flow in the well. And excuse me, if anyone is unmuted, could you please mute yourself? So I mean, there's a sound like sometimes it show up, and that's kind of, yeah. So in matrix acidizing, the acid treatment is injected at matrix pressure, or as I told you, below the fracture pressure. And in the fracture acidizing, which is like at least significant portion of acid treatment, is intentionally pumped above formation pressure or above formation fracturing pressure. And the fracture pressure or the fracture acidizing is only used in carbonate, and we do not use fracture acidizing in sandstone. And in the following slides, you'll understand why the acidizing is critical in sandstone more than or rather than carbonate. So before I start talking about sandstone acidizing or talking in details, it's very important to diagnose the issue that you have, because well stimulation is not like a solution for all the problems in the oil industry. And it has been said that if you know the problem, you are like halfway of your solution. So detecting the problem is quite important before you decide to go with acidizing. So starting with the production test, I believe this is the best way to know if you have a problem, assuming that it's a mature field, and there will be like three possible outcomes after testing the well. Okay, so we either have the decline in the liquid, we have a liquid decline, or sometimes we don't have a flow at surface. I mean, the well is not able to produce. And the third one, there is no decline in the liquid. I mean, the liquid is stable. So these are, here we have the main three categories for our case. Theoretically, the liquid should remain constant, but because like for many reasons, we might have a decline in the liquid. And sometimes there is no flow at surface due to many reasons, as we will see in a minute. But if you are lucky, I mean, there will be no liquid decline. So let's go on for each one of them, starting with no liquid decline. If you have no liquid decline, that means we need to check further if the oil is constant or if the oil is declining. So if the oil, in the case that the oil is declining, that means, I mean, if there's no decline in the oil, which is this case, that means we are on the safe side and we're doing pretty well. But in the second option, which is we have a decline in the oil, which is pretty much will be due to water production because of relative permeability change issue. So in this case, we need to know the source of the water. And there are, a couple of techniques that that's being used nowadays. For example, some of these techniques are applying is the production logging tools or any production logging to know the contribution of the produced fluids for each interval. So that helps you identify the intervals that produces water and which intervals that, I mean, they don't produce, or the interval that only produces oil. It helps you diagnose your issue. Also, you can put a tracer into the injected water and, follow that tracer to see, when and where is being produced. So this is another technique that uses to find out if there is, the source of the water. Where is it coming from? And also, there is a diagnostic plot called Chan graph. Can help you identify the watered out zones. If the water is coming from the bottom due to water coning, or the water is coming like from the edge, like channelings. Obviously, if the water coning usually occurs due to excessive liquid production. So the first thing comes to your mind, if it's water coning, the first thing comes to your mind is the water shutoff. Isolating the layers that produces mainly water. And as you may know, that there are different techniques to isolate the layers, either chemically or mechanically. Sometimes you need to inject polymers to isolate that layer, or sometimes you need to isolate to do the isolation by mechanical, by cement squeeze or bridge plug. All these things can help you isolate the watered out zone. So this is the case of water coning, or sometimes it's channeling. And this situation is a bit difficult. And in this case, we need to know the nearby injectors and what's the effect of each one of them by doing, for example, interference test. So we do interference test between injector and producer to see what is the effect of each injector on the producers, either for water production or for the pressure of the reservoir pressure in general. And according to that, we might need to reduce or choke back the nearby injectors, and of course that by keeping an eye on the reservoir pressure and monitoring the optimum voidage replacement ratio. So this is in the case of we have no liquid decline, but we have an oil decline. This is the first category. Going back to the roadmap, and the other two cases will be treated as the same. Following we believe that they have the same diagnostic approach. Okay, so as a reservoir engineer, we should always be aware of all the operational fields that took place, starting from drilling and workover history. And this is one of the most important parts, because here you will review any sort of damage that were introduced into the reservoir. And if we click here, this will bring us to the chart of the damage assessment. Because of the presentation time, it's not possible to go through each one of them, but briefly, there are two sort of damage we might have in our reservoirs, okay? So starting with, we have natural damage and induced damage. For the natural damage, usually due to production, for example, in unconsolidated sandstone reservoirs, which is with high pressure drawdown, so it's typical to produce sands, and that therefore blocks the perforation and harming the artificial lift integrity if you are producing with ESP. So this is might affect your productivity. Another issue is the clay swelling due to water production, which definitely reduces the permeability of the reservoir. And sometimes you have some minerals in your clay, and these minerals are, can be mobilized and migrated, and therefore reducing the permeability. Many times the damage is induced, in form of drilling. There is no need to mention that in the cases of mud losses, that causes, invasion of solids and filtrate into the reservoir, which pretty much plugs the flow paths. So the flow will be either restricted or sometimes prevented from the flowing. It depends on the overbalance pressure. And sometimes you might be surprised that the overbalance pressure reaches a huge difference between the mud pressure and the reservoir pressure. Another type of damage is the perforation. Under the best conditions of the perforation, you will destroy the original permeability. I mean, it's been said you will destroy up to 60% of the original permeability. And also that yields a compacted porosity. And in addition to that, if the perforation number of shots actually, if it was not well optimized, a new damage can be arise because of what we call the conversion scan. Another thing, and I think it's many problems comes from injection, because once we inject water, we are actually introducing a new fluid to the reservoir with different pressure and temperature, and which causes to what we call pH change. And this is creates a scale buildup and reduces the permeability. Another thing, if the salinity of the injected water is not compatible with the formation water, it may introduce a damage to your reservoir. And there are many other things, for example, emulsions. If there is emulsion that restricts the flow, if you have, as I told you, fine migration, if you have a scale buildup, any kind of scale buildup because of oil composition or because of injected water, sometimes you do a previous stimulation job causes, introduces another kind of damage. So all these things, must be addressed before you start talking about acidizing. So let's go back to our roadmap. Okay, so after reviewing the drilling history and shed the light on the damage that have in your reservoir, now it's time to know whether the problem is a mechanical problem or a reservoir problem. The mechanical issue will include either well integrity and the artificial lift. So we can check the well integrity by running slick line drifting to the total depth and check if the perforations are blocked or not. Sometimes they are blocked by sand fill or the scale buildup. So we need to get rid of these obstructions to the in the perforations. And sometimes we need to check the cement bond through CBL and VDL logs to help detect, if there is any potential casing leaks, or sometimes we have the flow behind casing. And actually, any production logging can helps you identify if there is, production, if there is a casing leak or flow behind casing. After checking the well integrity, then we go to the artificial problem. Whether you have no matter what, what's the type of your artificial or what's the method of your lifting system, if it's like ESP or gas lift. For example, with ESP or electrical submersible pumps, there are usually downhole trisenses that gives you a good idea if you have a mechanical or reservoir issue. And that's actually by knowing different factors. For example, by understanding the flowing bottom hole pressure, BWF, and the drawdown between the reservoir and the BWF, the dynamic fluid level, if it's like shallow or deep, and all these things helps you understand if the problem in the artificial, sometimes the design or the number of stages are not like well designed for this well, and we need to reconsider the design in that well. So that's why the problem might not be due to reservoir issue. Okay, so that's why we need to understand the all mechanical issue are going. I mean, there's no any mechanical issue before we move on to the following step. So if you guarantee that there's no mechanical problem, now we start about thinking about the reservoir. And as you may notice that I kept the reservoir section at the very last section. Why? Because when it comes to the reservoir, that means you will pay a lot of money. So before you pay, before you invest your money, you have to make sure that that all mechanical integrity are well integrity, and there is no artificial lift, and all sort of things you have to make sure before you go to the reservoir. So the first thing you do in the reservoir, you need to review all the petrophysical properties. That includes the porosity, the permeability, I mean, the conventional core analysis. In general, you review any formation test that is being done for that well. For example, if there is RFD data, if there is well logs, and you can also compare it with the offset wells. So all these informations helps you to evaluate the potential of the well. I mean, is this well really promising or not? Sometimes there is a problem in a well, but the well is not really promising. Why should I invest money into something that is not promising? And then review the reservoir energy. By checking, downhole reservoir pressure, like if we make sure that if the reservoir pressure in the optimum condition or not. Sometimes we only need to enhance the reservoir pressure by injecting water into the reservoir section, or increasing the injection to reach the optimum reservoir pressure, which is the pressure that provides the optimum voidage replacement ratio. And by the way, if you don't know what's the VRR, or you don't know what's the optimum reservoir pressure, and I have another webinar that talks, I mean, in details about how to optimize your field and what's the optimum VRR and the optimum voidage replacement ratio, and it might be provided by the end of this webinar. So if you make sure that all these things are, going pretty well good, so now and only now we should think about reservoir integrity, and this leads us to investigating, the reservoir issue, which is the skin analysis and the productivity index. Skin effect is, as interpreted from pressure transit analysis, is aggregate of several factors in the near well bore region of the reservoir. And, formation damage is one of the components of the total skin effect. And it's quite important to differentiate between the skin factor and the skin effect. The skin factor is actually a dimensionless number, and that is, distorts the physics of the fluid flow in the porous media. And the skin effect, this means the exaggeration. I'm not sure if it's right. That exaggerate the drawdown required to produce at a given rate. So therefore, the magnitude of the skin factor could be misleading, because many times we have the same pressure drop with different permeabilities. So therefore, we must make sure that the source of skin is the damage. So sometimes you have high number of skin, but that doesn't mean you have damage, because damage is only a part of the total number of skin, but sometimes you have a very poor permeability. So that's why you have a huge drawdown. So making sure that the damage is the source of your of the high number of skin. In fact, there are many calculations we can do to help us to diagnose the skin type, but these calculations are only like theoretical things. But when it comes to reality, you cannot, trust these calculations a lot. Okay, but generally speaking, if the damage is due to, let's say, partial completion, we can do something called reperforation. I mean, sometimes the damage of partial completion, that means the perforation is not covering the whole section of oil. So that's why there is a skin arise due to what we call it, the partial completion. So in that case, we do reperforation. I mean, we add another perforation, and just be aware of the distance to free water level and the distance to gas oil contact if you have gas, to avoid any water and gas coning. And if the case, the skin is due to damage, so now we can say we need to do stimulation. Okay, so as we said, there are two types of stimulation. There are fractures, hydraulic fracture and acidizing. And as a rule of thumb, oops. And as a rule of thumb, like if you have high permeability and good original petrophysical properties in general, it's better to go with acid job. However, if you have tight formations and very low permeability, so the first thing comes to your mind is doing hydraulic fracturing. So this is a very general thought about, selecting stimulation method. So now you understand what is the problem and you follow the problem starting from the drilling and workover history and the damage assessment. Then after that, you go to the mechanical integrity. You make sure that the well integrity is going well and the artificial system is well designed. And then you review the potential of the reservoir. And finally, you end up with, well testing analysis, and you start to propose, one of the stimulation treatments. Okay, so let's see how does it look like in sandstone. Okay, in sandstone, the acidizing in sandstone, you really want to dissolve some of the damage, like whatever the damage has been created, either by drilling, fluids, or being produced, or any sort of chemical reactions. So you need to get rid of all these damage assessment. And it's quite important to highlight that sandstone oil reservoir consists of different clay minerals, such as kaolinite, smectite, or sometimes illite. These are the most common clay minerals. They exist in sandstone formations, and these minerals are highly affect the formation damage during the well stimulation operations. And the interactions of clays and other minerals with fresh water and a strong HCl could result in different things. They could result in dissolution, could result in precipitation of insoluble materials, and sometimes could result in fine migration or clay swelling. So all these things may affect the stimulation process. So in sandstone, what we do, it's, talking about the matrix acidizing treatment, should be designed primarily to remove or dissolve the damage or blogging in the perforations and the, formation near the well pore. And theoretically, the acid, as you can see here in this picture, the acid flows through the pore system, dissolving solids and finds that exist in the pore throats that restrict the fluid flow. And if there is one thing you should know in sandstone treatment, is that the sandstone acidizing treatment has a chance for success only if the acid removable blogging or formation damage is present. There must be, so the acid in sandstone, it's more about damage removal. It's not exactly a stimulation. So that's otherwise, if there's no damage in your reservoir, so this is what introduce a new damage to your reservoir. So that's why in the beginning of the presentation, I try to define what's the main issue or the main problem. In sandstone acidizing treatment, you need like a mix of two things, hydrofluoric acid and hydrochloric acid. And in the old days, people started with 12% of HCl or hydrochloric acid and 3% of HF or hydrofluoric acid, and was called like a regular mud acid. And this is a Schlumberger term. And like if you deal with Halliburton's, for example, they say an HF acid, which is exactly the same, just different names. And once we introduce the mud acid into the sandstone formation, the hydrochloric acid would be hardly spent, but all the HF acid would go away. So the end of the result and as a primary reaction will have something like 10% of HCl and 0.1% of HF. And also will a combine of ammonia and silica and silicon fluorides, and this is the primarily spending of HF. Okay, so as you may notice that not all HCl is being reacted, because there is 10% left. And people thought that at first people thought that is nothing else is going to happen. I mean, this is the final reaction. But then they found out that there is a second stage of HCl spending, and this stage, high percentage of hydrochloric acid was left, and you end up with 4% of HCl and the same amount of HF, which is 0.1% of HF, with a large amount of ammonia fluorides. And unfortunately, you will have silicon and flow silicate will precipitate in the second stage. So these are insoluble materials, and if the second reaction occurred, so probably or not probably, they will precipitate, and they are insoluble, and they will reduce the permeability. And finally, there is a tertiary spending stage. This, like 4% of HCl and 0.1% of HF, will be reacting even further to spend like all HCl and HF, and you end up with a solution that is very high aluminum fluoride compounds. And in fact, you will have a risk of precipitating and scaling in the well pore. So you only want to have the first reaction, and otherwise, if the design of the acid was not properly designed, so that's may affect your reactions, and you will end up with the second and tertiary reactions where you will end up with insoluble materials. Always remember that to remove all the carbonates in the near well pore area, because there's one thing that you never want to have around the well pore when you treat a well with HF acid, and this is the carbonate. If you have carbonate, you have to get rid of it before you inject HF, because calcium and magnesium are salts of hydrofluoric acid, and they are insoluble, and you will create a lot of damage by precipitating these two salts. And to prevent this, you can have HCl pre-flush and use that to remove all, as much as possible of carbonates, about like 2 feet away from the face of the well pore. And we do that by pumping HCl ahead of mud acid as a pre-flush, usually 15%. And as you can see here, so this is the thing that we do as a pre-flush. We inject HCl to get rid of the carbonates, and then after that we inject the main flush. So here in this chart, according to the percentage of carbonate that you have, so you will need a specific volume of pre-flush to remove that carbonate in your reservoir. Okay, so for example, if there is like 3% of carbonate, so you will need to inject about 50 gallons per foot. While, for example, if you have more than 10%, you will better treat it as a carbonate rock rather than a sandstone, because you can see the percentage is higher than, if the percentage is higher than 10%, so the volume would be more than 250 gallons per feet. and it goes off the scale, and this is not going to work. So it depends on the percentage of carbonate. You will need a volume of hydrochloric ahead of the mud acid. Otherwise, if you inject HF and you have carbonate, so you make the thing very, very complicated for you. And sometimes such kind of wells are, can barely be reactivated again. And then after that, we have the main flush. The main flush where HF reacts with, the clays, the main flush, which is HCl plus HF. And the HF, or hydrofluoric acid, reacts with clays and fines, reacts with the drilling mud cake, reacts with the silica to improve the near well pore permeability. And the objective of HCl and the mud acid is to keep the pH low and helps to prevent the secondary HF reactions, the one that I was talking about. And after that, there will be an overflush. Displacement actually is for, acid, flushing the acid away from the well pore. Sometimes we use nitrogen, and sometimes we use weak HCl and, NH4Cl or ammonia. So based on a lot of research, there are a couple of recipes that have been proposed that was being used for quite a long time. So starting with what I call a regular mud acid with 12% of HCl and 3% of HF. And in fact, it's not being used anymore because mostly we are using these days 13.5 and 1.5 or even less, especially if you have a feldspar around. So you might need to go even down with 9 to 1 of HF. These are, the recommended volumes, and we are actually have different volumes, depends on how much or how bad your reservoir is damaged. And generally, we higher the volumes with lower concentrations. Okay, so it depends on the volume that is going to be injected, and it depends on your permeability. It depends on the damage. I mean, what type of damage? That's why we have to understand the reservoir before we start designing the acid. So this is the general thoughts about sandstone acidizing. Here we have the carbonate formation. The situation is entirely different because the reaction is really simple. First of all, it's the acid reacts with carbonate to form water and CO2. And the CO2 comes out of the solution if the pressure is below 70 bar. And if the pressure is over 70 bar, it remains in the solution. And for dolomite, is slightly different, but the reaction is almost the same. The principal products are water and CO2, and the rest remains in solution. So there is no a risk of insoluble material. So that's why you feel very comfortable when you apply acidizing in carbonate. But in sandstone, you will think twice or sometimes 10 times before you do acidizing. So the essence of carbonate acidizing is that you promote formation of wormholes, and the acid enters the carbonate rock and form a little wormholes, and that can range from few centimeters to 2 meters in long. So it could yield a skin up to -2. So this is exactly a stimulation process, because even if you don't have a damage in your reservoir, you can create a new wormholes and you can stimulate a well. So in sandstone, you can never ever have a stimulation with minus. I mean, it's more about damage removal. But in carbonate, you can stimulate the well and you can have a minus skin. And once you have a minus skin, that means you are actually stimulating the well. The thing that you should pay attention to it is that in carbonate, there are different factors, which is the reaction rate, and the injection rate and the diffusion rate. And the best wormholes that you have when you get like high reaction rate with a low diffusion rate. So the reaction rate is not, spread in your reservoir very fast, and you can actually get things. You can actually achieve this by adding some additives, for example, emulsifiers, or make it, more viscous. So this is the main thoughts about carbonate. So once we decided to do a matrix acid treatment, the first thing we do is doing some tests to ensure that the stimulation will not add a new damage to the reservoir. The first test is a compatibility test between the reservoir fluids and simulation fluids. So why we need to do that? Actually, because of the tendency of these combinations to cause a damage into the wellbore if they are not actually compatible. And then we have the solubility test, understanding how the reservoir rock may react to this injection is like quite important to ensure that the damage in the reservoir formation does not occur, and also helps us to understand if the permeability could be improved or not. So the first, we do the test. Actually, these plugs are measured for the porosity, density, seismic wave velocity, and the permeability. And then the samples then exposed to the first to HCl acid, hydrochloric acid, and second to both, like the mud acid, which is initially HCl treatment, followed by HCl-HF. And after that, we observe any physical change that occurred in the blood. Okay, and then we do another test, is a corrosion test to avoid any harming of the well integrity and any corrosion problems. And as you will see maybe in the following slides, that the acid design should not be the same for all rocks. Sometimes it would be more confident, like with a sandstone, and you will be less confident. You will be more confident with carbonate. I'm sorry, but when it comes to carbonate, as I told you, it creates a new wormhole, so you don't worry about the damage. And then talking about the additives, the main idea behind additives is to get over any suspected issue may arise while injecting acid. For example, the corrosion inhibitor to prevent corrosions, or sometimes you need to do like diverters. In the case of heterogeneous reservoir, the permeability in a new reservoir is not actually homogeneous. So in this case, you need to specify the interval that the acid should enter these layers. So these are the main tests and additives that usually being added to the sandstone. Here we have the main elements that that participate in the success of this story. Okay, so starting with selection criteria. The thing that I was talking in the roadmap, it's quite important to make sure that this well is damaged and it requires to be stimulated. Another thing that you make sure that this well is it has potential, so there's a good reserve in that well, so it deserves investing money on that well. Sometimes for the selection criteria, I wouldn't choose a well that has high water cut, because I mean it's really difficult to control the acid movement, even though there are many techniques nowadays, but it's really difficult to control the treatment in a specific interval. So that's why high water cut and high sand production are not in a top priority in sandstone treatment. So this is the first element, is the selection criteria. And the second element is the treatment design. And the third one is the field operation. If only one of them was not like designed properly, in this case, the job will not be successful. So all of them, they are like completing each other and supporting each other. So that for the treatment design, this involves the volumetric calculations and recipes and the bombing sequence. You know, um, Staged treatment is like really common in sandstone or clastic stimulation to minimize the impact of unwanted secondary reactions. And the use of pre-flush and after-flush has proven to be like the best practice in sandstone. And then we have the volumetric. Volumetric requirements of like the main stage of treatment is determined first, and then after we determine the main volume according to the radius of the damage that you have, then the pre-flush and after flush volume are calculated subsequently based on these volumes, based on the volume of the main flush. The recipe includes all the acid additives. And this is actually one of the trickiest points in this topic, or in acid stimulation. Technically speaking, this is exactly the main reason why you select different company, because I mean, what's the additives that any surface company can provide? In fact, HCl and HF, or formic acid, citric acid, and all these things are standard acids. However, the additives are different for each surface company. So the design will be done according to the additives that surface company can provide. The first additive, as I told you before, the corrosion inhibitor, and there is no treatment without corrosion inhibitor. The corrosion inhibitor is actually a group of materials together, and the main goal of corrosion inhibitor is acts like as a barrier between the acid and the pipes, so the acid will not react with the casing or with any whatever you have, the pipes or tubing. So it prevents any reactions. And it's important to know there are different corrosion inhibitors with different acid types. For example, there is a corrosion inhibitor for HCl and a different one for HF, and another one works for organic acid. And you may ask, like, what's the best one that can be used? Actually, is by basically doing a corrosion test. So that's why corrosion test is quite essential. Another additive that we do is the corrosion inhibitor intensifier. In some cases where the temperature is really high, I mean higher than 250 Fahrenheit, and usually the corrosion inhibitor by itself is not enough, and it needs the assistance from other chemicals to enhance the corrosion performance. So there are different types of corrosion inhibitor intensifiers. For example, formic acid, I guess, and potassium iodide, and I think these are the most famous intensifiers in the industry. I would like you to pay attention that we only use additives if we need them. Otherwise, they can just cost you money and nothing more. So that's why you have to pay attention of all the additives, and you have to know what's the reason behind all these additives. Another one is anti-sludge agents. Usually, normally you can apply this kind of additives when you have asphaltenes in your well, and you add this to eliminate the asphaltene and to precipitate out of the formation. And there are many other additives usually being added, such as solvents and retardants, and to make the reaction last for a longer time. So there are many. It depends on your mineralogies, and it depends on your severity of damage in your reservoir. you can add these additives. And the third thing is the field operation. For the field operation, there are different techniques. Um, you can use a bullhead technique, which is like injecting the acid from the surface, which like the injected acid will go through the pipes, and it will be exposure to your production system, or just use cold tubing. So in the cold tubing, actually, there are pros and cons, and we will see that in the following slide. So this is the main three elements of success. The definition of success, actually, I've here it's different from one company to other. Sometimes, like some companies, they say that the acid job is successful if the production after the treatment is greater than before the treatment. So now we can say that the acid treatment was successful. Other companies will consider the incremental production if it's pay out the treatment cost within a certain period or not. So this is different perspectives for different, company policies. But normally for the NOCs, they consider this one. I mean, they don't really care about the production time because it's the payback time. I mean, because it's like big companies, and they don't really pay attention to the paying back time. While small companies, they consider the incremental production and they link it to the economical wise. Here is some advantage and disadvantage for the field operation. Actually, I don't have that experience in the field operation, but here that's what I found. Like for the cold tubing, you can control how much volume that can be injected, or you want to inject. So the volume is controllable. And another positive thing, that you can select the interval where you want to stimulate. For example, you have a long interval, let's say 100 is not that long, but 100 feet of interval, and the permeability is heterogeneous. I mean, so some layers have high permeability, while other layers are more, let's say, damaged. So you want to stimulate that specific layer. In that case, cold tubing might help you. Another thing is like suitable for long intervals, and variable, as I told you, if you have different permeabilities. The negative is like small volumes, so you will need a lot of time to spend to inject a certain amount of volume, because I mean the volume is controller, but only a small amount is allowed to inject, and obviously is expensive. For the bullhead, actually, it's the advantage of it is large volumes need to be injected. The bullhead is very good technique, and it's not really expensive. But the main disadvantage of the bullhead, that is exposure of the whole completion to the acid. Even though you are using a corrosion inhibitor, but sometimes it doesn't work properly, and it's too much pressure at surface. So these are the main pros and cons for the operation. So this is all for the this webinar. Thank you so much for your patience. I try to make it, very brief and very general piece of information, because like each topic, it might be extended, and you can talk about like an hour for each slide. But thank you so much.
Thank you so much, Mr. Abdurahman. Guys, if you have any questions, you can ask, you can unmute yourself, or you can write them to the chat box. I will read them. Already we have some questions. Can I read them to you? Mr. Abdurahman?
Okay, let me read the questions here.
Yeah.
Okay.
First one is what distinguishes an acid wash from acid fracturing with regard to regulation?
What's the distinguish an acid wash from acid fracturing with regard to regulation? Well, basically, the acid wash, that means you are only cleaning the well pore, okay? So it's more about placement. You just place the acid into the well pore, and the well pore reacts with whatever you have, like scale or anything, because you will take a sample of the thing that's restricting the flow, and you check it with what's the best acid that reacts with this scale, and then you remove that scale. For the acid fracturing is is completely different, because you are not interested, and you are not only interested in the well pore, but you are interested in far away from the reservoir. I mean, more than 5 feet of the reservoir. So that's why you need to inject in a pressure above fracture pressure. And as I told you, in sandstone, fracture pressure, it's like it's not recommended to do acid fracture in a sandstone formations. But yeah, so they are totally different. But I didn't get you. What do you mean regards to the regulation? Um, could you please like clarify in the text below if I didn't answer your question properly? Let's go to the second one. For sandstone formation, can we use both HCl and HF? If both of them are okay, then based on what we select the acid type. Okay, maybe you came late in this webinar. In sandstone, we use the acid is being mumbled in different stages. There is a pre-flush and the main flush and overflush. Why we do pre-flush? We do pre-flush to get rid of any materials that may be affected by HF. For example, in the pre-flush, we inject only HCl to get rid of the carbonate, and then you inject the main flush. And in the main flush, we have HCl and HF. And after that, you have an after flush or overflush and in the overflush, you want to circulate the injected fluid out of the well bore and produced away from the reservoir. Why you want to produce away? Because you want to avoid the second and tertiary reactions. And actually, there are many criteria to select the type of acid. For example, there are sometimes it depends on the mineralogy of your reservoir. If you have carbonate, you cannot inject with HF. Sometimes there are these are, but for sandstone, we use mud acid, HCl and HF. I mean, you cannot use HCl only in sandstone formation. The third one sounds like, that the matrix acetizing efficiency depends on many parameters, such as acid composition. Yes, its design, considering geological, physical, and technological parameters of the productive reservoirs. Exactly, yes. Among the possible low efficiency reasons of acidizing treatment is the predominant supply of acid to highly permeable intervals with high water saturation, which loads to the I'm sorry if it's like, is it a statement or relation? In carbonate reservoir, we can use various modified acid compositions such as viscoelastic surfactant based on self-diverting acid evolved to provide improved matrix treatment. The question is, okay, it's a very nice. The question is how can we enhance the acidizing treatment in sandstone reservoir? Is there any chemical reagents that guarantee assimilation treatment? Well, no one can guarantee anything in stimulation because there are many factors. I mean, there might be a minor factor that affect the whole system. Sometimes you you have a very good design and you bring like a best surface company with high technology, but you didn't choose the right well to be treated. So that's why understanding the problem is really critical. And sometimes you propose the best candidate well, but the design is not well designed. So that's why in sandstone makes it even little bit complicated because of the clay minerals and because of the second and tertiary reactions. And actually, you are not talking about the acid itself. You are talking about the time that is required to get rid of the injected acid. So all these things may affect. So as a rule of thumb, I mean, as far as I know, that the in sandstone, about the percentage of success is about 60% around the world, and this is based on an SPE paper was made in Nigeria. But there is no something that can be added. It's an integration process. There's no one thing that you can add to sandstone reservoir to guarantee the success of the story. Who's responsible to design the intervention concentration? Well, it should be production or okay, that's a good question. In the project that I am actually working on nowadays, because nowadays we are performing stimulation treatment acid in sandstone. Actually, we are a reservoir team, but we are not the one who make this the recipe. But we understand the reservoir. We know our problem. We know our reservoir more than the surface company. So we explain our problem to the surface company, and the more the surface company understands the problem, so the better solution they can support. So it's the design is being done usually by surface company, by, let's say, Schlumberger, and the design, it could be adjusted because of the more information you provide, the more accurate can be done. So it should be a reservoir engineer who's doing this. It's not only a reservoir and production engineer both together. Yep. I think there's no more questions. Thank you so much for your time, and I'm sorry for talking. I don't know, it's more than an hour now.
No,
thank you so much.
Thank you so much, Mr. Abdurahman, for to accept our invitation to organize this meeting, and also thanks to the participants for their time, also for your time. If there is no question, we can end our session if you want. Mr. Abdurahman, can you hear me?
Yes, thank you so much.
Thank you so much. We can, I guess, finish our meeting.